about the transport of gases in the blood. And this is really going a step further from what we talked about in terms of diffusion. So when we looked at diffusion, we were really talking about those partial pressures and how that gradient was set up to actually move the gases through the circulatory and pulmonary systems. But today we're going to speak about how these gases are loaded and unloaded to hemoglobin specifically, and then the other mechanisms for transport as well, okay? So we'll start off by recalling the fact that we said oxygen is not very soluble in the blood. This is something we spent quite a bit of time when we looked at those beakers establishing this fact, right? Oxygen does not move around very well in the blood. And so we've got this hemoglobin that is crucial to the movement of oxygen around the system. So only 1.5% of our arterial blood has oxygen dissolved in it. This is so little that if we were to rely just on this amount alone, our cardiac output would have to increase about 50 times what it currently is in order to adequately oxygenate all of our tissue. So this is very insufficient in terms of the amount of oxygen that we need. So the remainder of the oxygen to meet our demands is circulated using hemoglobin. And we talked about this reversibility of hemoglobin. Hemoglobin is that 4 subunit protein molecule that can bind oxygen onto those heme groups that we looked at previously, and it can do so reversibly. So it can bind oxygen tight enough to move it around the system, but not too tightly that it cannot be dissociated when it gets to the tissues to oxygenate those tissues. So we've got this reaction, and we've got these double-headed arrows that indicates the bidirectionality here. On the left, we've got deoxyhemoglobin, which is the hemoglobin not bound to oxygen. And on the right, we've got oxyhemoglobin, which is the form when it has those 4 hemoglobin molecules bound. Now, what we can see in this image is the partial pressure of oxygen across the alveoli. And this is facilitating the diffusion of oxygen from alveoli into the pulmonary capillaries. And if you look more closely at what's happening here, this is the alveoli, this is oxygen, it's moving across this membrane, which is the alveolar cell, the fused basement membrane, and the capillary cell. What do we call that membrane? Just for review. What do we call those 3 structures? The respiratory membrane, I'm hearing it right. So the respiratory membrane. So oxygen is moving across the respiratory membrane here. It's gonna move into this erythrocyte. It's gonna bind on to hemoglobin, and it's gonna circulate through our systemic arteries, eventually capillaries, and then eventually at the tissues. If we look more closely at what's happening at the tissue level, we can see the opposite happening, right? Oxygen dissociating off of hemoglobin, crossing the capillary bed and moving into the tissues where it's being consumed for cellular respiration. So it's really important that hemoglobin bind oxygen reversibly, and we're going to move on today to speak about what influences the different states of hemoglobin. So what tells hemoglobin to want to bind oxygen, and then what tells hemoglobin to want to let it go when we get to the level of the tissues. Okay, now we know hemoglobin can bind 4 oxygen molecules. It's got 4 heme groups in the center of those subunits, and we can bind an oxygen each. And so when we look at the law of mass action, this law states that if we've got more of our reactants, we'll drive the reaction towards products. And if we've got more products, we'll drive the reaction towards reactants. Okay, so if you've got more oxygen around, we're gonna bind more oxygen to hemoglobin. We're gonna create more oxyhemoglobin. And if you've got more oxyhemoglobin, we'll drive it in the opposite direction to create more deoxyhemoglobin. And so at complete saturation, hemoglobin has all 4 of its subunits, so all 4 of its heme groups in those subunits bound with oxygen. And this can go back and forth depending on a few factors that we'll speak about. Okay, so the saturation of hemoglobin is really an important factor that we're gonna determine. So this is it in its 100% saturated state. Okay, everyone good here? Any questions? All right. So let's look at what's happening in terms of hemoglobin and it becoming saturated versus unsaturated. So we know that when we have 100% saturation, hemoglobin has the ability to carry 1.34 milliliters of oxygen. And typically in an adult human without any sort of pathology or anemia, we have anywhere from 2 to 17 grams per deciliter of hemoglobin. So if you multiply those factors, the oxygen carrying capacity of hemoglobin is about 200 milliliters of oxygen per liter of blood. That's how much oxygen we have circulating in a liter of blood. And we can even go a step further and talk about our cardiac output, right? We know cardiac output to be what? Okay, stroke volume times heart rate, but in terms of a quantity, how much, does anyone remember? It's kind of a stretch. 5 liters, right? So we got 5 liters per minute circulating, and we've got 200 milliliters of oxygen per liter. So we've got 1,000 milliliters of oxygen circulating our body per minute, okay? Now, if we look at the different states of hemoglobin, when it is 100% saturated, or actually it's 98% saturated because all of the hemoglobin aren't actually bound in actuality, but we can think of it as being 100%, as being full. This is in our arterial blood. What we see is that each of those subunits, each of those heme groups has an oxygen bound to it. We can see that here, with the exception of a few. That's why this is not fully 100, but for our purposes, we'll consider it to be 100, okay? And so at a partial pressure of 100, which we talked about, that's the partial pressure of oxygen in our systemic arteries. Hemoglobin has most of the subunits bound with 4 oxygen molecules. Now, when we look at our venous blood, when hemoglobin is about 75% saturated, we don't actually lose all of the oxygen, right? We only lose 1. So in the unsaturated form, hemoglobin is only releases or only loses 25% of its oxygen carrying capacity. That's a really, really important phenomenon. So hemoglobin is never empty, all right? It's never completely lost all of the oxygen molecules bound. Can anyone think of a reason why that would be important? Can we think of a reason why that would be important? So even in deoxygenated blood, even in our systemic veins, we've still got oxygen bound to hemoglobin. So yep, that's part of the answer. So it's going to help to drive the reaction in the opposite way. It's going to help with the state of hemoglobin to move towards going back to the lungs. But something else in terms of protecting our tissues. So this is actually another one of those protective mechanisms, okay? So we can increase our metabolic demands, right? Tissues can increase their metabolic demands up to 4 times, and we still have adequate oxygen to supply. So at rest, our tissues are only requiring 25% of the oxygen that's being circulated. And so in instances of an increased metabolic activity, exercise, a fight or flight response, we have lots of oxygen circulating as a backup reservoir for increased metabolic activity, okay? All right. So this brings us to the oxygen hemoglobin or hemoglobin oxygen dissociation curve. So this is how hemoglobin changes its shape, changes the way it behaves, depending on the partial pressure of oxygen and how it loads and unloads those 4 oxygen molecules. So we'll describe this here a little bit and then we'll illustrate this. We're going to do quite a bit of drawing because we're going to draw out some different scenarios here. But let's go through this here to start. So on the y-axis, we've got the percent of oxygen saturation of hemoglobin. And that's a really complex, fancy way to say how many oxygens are bound on that hemoglobin, whether it's 1, 2, 3, or 4. okay? On the x-axis, we've got the partial pressure of oxygen. Again, another fancy way of saying how much oxygen is present, right? Depending on where we are in veins, we've got less. In arteries, we've got more. And then if we look at the way that this curve behaves, it's not a direct or a linear relationship. It's actually more of the sigmoidal curve. And that's because when we bind one oxygen, right, so about 25%, right, because we know 1 out of that 4 is 25% saturation. If we bind one oxygen here, we automatically have this conformational change in hemoglobin such that it increases its attraction for oxygen. And so the other 3 oxygens are going to bind with much more ease because of that change in conformation. So we see this more steep curve as we bind those second and third oxygens on. And then when we get to the top here, as we've bound that third oxygen, we see the graph flattening off because we now have less spaces to bind, right? We've bound that third oxygen on. And so the graph flattens off as we get to that fourth oxygen. And as we talked about on the previous slide, we really only change the this final quarter, this final state of hemoglobin is what we change, because we're really only using this 25% of the oxygen that's bound here. So in healthy tissues, we're going to unload just that one oxygen and we're going to keep hemoglobin